Hello, this is first part of sixth lecture of linear algebra, and this part is about orthogonal transformations and orthogonal matrices. Okay, uh, let us consider linear operator in n-dimensional space T, and we can observe that usually linear operators do not preserve length or angles of vectors. Okay, this is very easy to check in basic examples. Let us consider one such example. We take a linear operator from two-dimensional space to two-dimensional space, basically given by this formula. Yeah, this formula implies that this matrix 1, 2, 0, 1 is a standard matrix of this linear operator T. Yeah, and if you substitute here instead of x1, x2, if you substitute vector 0, 1, you see that vector 0, 1 goes to vector 2, 1. It's basically the second column of this matrix here. But vector 0, 1, this is vector e2 in our standard basis of R2. This vector has length 1, yeah, almost by definition. You take a dot product with itself and divide, yeah, and you get 1. Yeah, so it's take a square root of this dot product. This is 1. Yeah, okay. So vector e2 has length 1, but vector t of e2 has length root of 5. So length is not preserved by a linear operator t. Also, you can check that this linear operator change angles between vectors. How to see this? So, for example, you take vector e1 and e2. They are orthogonal. Yeah, orthogonal means the dot product is 0. E1 and e2 form orthonormal basis of two-dimensional space. But vectors t of e1 and t of e2, they are just columns of this matrix, first column and the second, respectively. So their dot product is 2, it's not 0. So these two vectors are not orthogonal. So angles are not preserved, similarly like to length. So this is not very surprising. There's no reason why linear transformation should preserve length and angle of vectors and between vectors. Yeah, this brings us to new definition. We say that linear operator is orthogonal if orthogonal transformation. Yeah, if this linear operator preserves dot product between vectors. What does it mean? It means that for every vectors x and y in Rn, t of x dot t of y is the same as x dot y. Yeah. So you take any two vectors, you take the dot product, and this should be the same as the dot product of the images t of x and t of y. Okay, this is very nice definition. Sorry. Okay, so immediately from this definition, we conclude that orthogonal transformation preserve length of vectors. Indeed, so if you take vector x and you apply t of x to it, yeah, you get this vector t of x. Then what does it mean? What is length of this vector? By definition, length of a vector is a root, square root of dot product of this vector with itself. So length of this vector t of x, it's a root of t of x dot t of x. But by orthogonality condition, this is the same as x dot x. So this is root of x dot x, but root of x dot x, it's by definition length of vector x. So length are preserved. Absolutely in the same way, you can prove that orthogonal transformations preserve angles between vectors. Why? Because by definition, angle between vector x and y, it's a such angle between 0 and 2 pi, such that cosine of this angle is x dot x divided by the length of x and length of y. Okay, so if you know dot product between two vectors, if you know their length, you know the angle between them. So this implies that orthogonal transformation preserves angles. Okay, good. Surprisingly, the opposite assertion is true. We know that orthogonal transformations preserve length, but if we have a linear transformation, linear operator, which preserves length between vectors, you can actually deduce that it's orthogonal, which is a bit surprising, but this is not hard to prove. let us prove this here. Okay, this is basically, this follows from this lemma. If you take two vectors x and y in n-dimensional space, then the dot product between them can be expressed as by this formula using only length of these vectors. Yeah, x dot y is 1/4 of x plus y dot x plus y minus x minus y dot x minus y. Yeah. So here on the right hand side, we only have length of vectors x plus y and x minus y. On the left hand side, we have dot product. So if you know this lemma, you can deduce that linear operators that preserve length of all vectors in n-dimensional space must be orthogonal. Indeed, the right-hand side going to be preserved when you apply t. So this means that left-hand side also should be preserved when you apply t. Okay, how to prove this lemma? Okay, to prove this lemma, you just basically expand the right-hand side, which I already implicitly did. Yeah, you just rewrite the sum as a dot products, and then you simplify, and you get 4 times x dot y. Okay, this is very handy lemma, and it will be used from time to time in the future. But this lemma basically doesn't tell us, and this property doesn't tell us how to check orthogonality, because in reality you cannot go through all vectors and check that t preserve length of every vector. Yeah, this is not possible to do. Surprisingly, we have very nice criterion for orthogonality of linear operator, which is can be checked easily if you know the standard matrix of linear operator. Let us preserve this criterion. Yeah. Okay. This is criterion I was talking about, orthogonality criterion. If you have linear operator and you fix its standard matrix, then the following 5 conditions are equivalent. First condition is linear operators orthogonal. Second condition, columns of the matrix A form an orthonormal basis of Rn. And third condition, that the rows of matrix A form orthonormal basis of Rn. And the fourth condition, that you have this nice equality, A transpose times A must be identity matrix. And fifth condition is symmetric. A times A transpose its identity matrix. In particular, this means that transpose of a matrix A is the inverse of matrix A, which is very handy. So basically, in particular, this means that if your linear operator is orthogonal, then it's very easy to find the inverse of its standard matrix. Here you just need to transpose it. Yeah. And it also means that it's easy to find the inverse of this linear operator. You should take linear operator given by the multiplication by the transposed matrix to the standard matrix of T. Okay, good. This is very handy criterion. Any of these condition 2, 3, 4, and 5 is easy to check. Yeah. Okay, let me give this nice example. If you take a matrix which we already met many times earlier, this is a linear operator. This is basically rotation by angle theta, clock counterwise around the origin. And as we already know from the previous lectures, its standard matrices give basically this cosine minus sine, sine cosine. And you can check that it's orthogonal. How to check using this theorem? You just multiply this matrix by its transpose, and you see that you get identity matrix. Basically, here you only use only one trigonometrical identity: cosine square plus sine square equals 1. Okay, good. So of course we know that rotation preserves angles. This is intuitively very clear. You can check it. But we can just use this criterion on this slide, and we give purely algebraic proof that this linear operator is orthogonal. Okay, Good. So let us prove it. This is not hard, but let us prove accurately. Okay. So first, we prove that condition 4 and 5 are equivalent. Let me remind you, condition 4 and 5 are very symmetric. One of them is A times A transpose is identity. Another one is A transpose times A is identity. One can intuitively think that one condition can be obtained from another by taking the transpose of, for example, this formula, but this is not correct. If you take a transpose of this equality, on the right hand side you get identity, but on the left hand side you basically get the same expression as before. So you cannot obtain this equality from this equality or vice versa directly by transposing. You have to use some other conditions. But let me remind you that earlier in the previous lectures we proved that to check invertibility of a matrix, if you have some matrix A and it's invertible, by definition, if this matrix B is such that AB is identity and BA is identity. But we proved that for square matrices, only one of these conditions has to be verified. So if AB equals identity, then this implies that BA also equals identity. We proved this earlier. So these two conditions are equivalent. So now using this invertibility criterion, you have, if you have this equality, then you must have this equality. You just swap these two matrices like here. Okay, this proves that condition 4 and 5 are equivalent. For example, let us prove that condition 4 implies 1. Condition 4 is A transpose times A is identity. We want to show that the corresponding linear operator is orthogonal transformation. How to do this? Okay, basically by definition, we have to check that we assume that this is true, that matrix A satisfies this condition, A transpose times A is identity, and we have to check that T of x dot T of y is the same as x dot y for every two vectors x and y in Rn. Okay, you just check this by definition. T of x dot T of y, this is nothing but ax dot ay. Yeah, because T of x is just a times x, where because a is a standard matrix of linear operator T. Okay, but then observe, if you have two vectors and you take a dot product, it's the same thing if you transpose the left vector and in this expression, yeah, and then just take a product of matrices. So this, it's a very handy observation, which actually used quite often in this course. We already used it in the proof of the last theorem of the previous lecture. Okay, this observation that dot product of two vectors is just a product of the first vector transposed and times another second vector. Yeah, so you have this, but then we have this very handy property of transpose of a product. Transpose of a product of two matrices, it's a product of the transposes taken in the opposite order. Yeah, so AX transpose, this is X transpose times A transpose. Yeah, so you have this, so this equal to this. But now we use the condition that this matrix A transpose times A is identity. So this is just identity. And since it's identity, identity times y is just y, you get this. But again, this product is nothing but the dot product of vectors x and y. So this proves that 4 implies 1. Condition 4 implies condition 1. Okay. To, for example, show that condition 1 implies condition 2, okay, let me let me remind you that condition 1 means that linear transformation is orthogonal transformation. But condition 2 means that the columns of the matrix A are orthonormal. Since there are n of them, it means that columns of matrix A form an orthonormal basis of our n-dimensional space. Okay, so we suppose that T is orthogonal. We have to check that the columns of the matrix, standard matrix of linear operator T for an orthonormal basis. Yeah. So we have this condition by definition: t of x dot t of y must be ax dot y. But t of x dot t of y, this is ax dot ay. Yeah. Okay. This is true for any vector x and y. If it's true for any vectors x and y in Rn, we can substitute instead of x and y here any vector we like. So we substitute vector ei here instead of x and vector ej instead of y. So then this equality, its special case going to be this. A times ey dot a times ej, it's must be equal ei dot ej. But ei dot ej, we know the vectors e1, e2 up to n, they are orthogonal and they are orthonormal. They form orthonormal basis of Rn by definition, almost by definition. Yeah. So this dot product is 1 if I equal j and 0 if I not equal to j. Yeah. On the other hand, what is a of ei and a of ej? This is just nth i's column of matrix A and j's columns of matrix A. Yeah. Again, when you multiply A times vector ei, this is ith column of matrix A. And A times ej is j's columns of matrix A. So what we just proved that ith column of matrix A and j's columns of matrix A are orthogonal if I is not equal to j, and if I equal to j, that the dot product is 1, so it means length is 1. By definition, this means orthonormality. Okay, so we prove that 1 implies 2. Okay, good. So now let us check that 2 is actually implies 4. Again, 2, it's a condition that columns of the matrix A are orthonormal, and the condition 4, it's A times A transpose equal to A transpose times A equals to identity. Okay, so we take columns of the matrix A, we denote them V1, Vn, and then we just check what is the entry of A transpose times A. But think about it. You have a matrix A, and this is matrix A, and what happens when you transpose matrix A? You just flip it around diagonal, so you get this matrix A. So it's just they square, of course, yeah. So when you take a product, this is the same as to take dot products of the rows of transposed matrix and columns of the original matrix. But rows of the transposed matrix, nothing but the columns of the original matrix. So when you take these products, its entries of this matrix is basically dot products of i's and k's column. Yeah, this can be expressed like this. So again, A transpose times A, you take its I kth entry of this matrix. This is nothing but the dot product of ith column and k's column of A, Vi dot Vk. Okay, and yeah, but this is by, if we, for example, if we know condition 4, this is identity. Yeah, identity matrix. So if you know condition 4, then this proves that Vi dot Vk is 1 is if I equals k, and 0 if I is not equal to k, which exactly means condition 2 orthonormality of columns of matrix A, and vice versa. If you know that this guy is 1 if I equal k and 0 if I not equal k, this means that the entries of this matrix are the same entries as the matrix of identity matrix. So this matrix is identity. Yeah. Okay. So this basically proves that second condition and fourth are equivalent. Absolutely the same way you prove that condition 3 and condition 5 are equivalent. Let me remind you, condition 5 tells you that A times A transpose is identity, and condition 3 means that rows of the matrix A are orthonormal. Yeah, this is basically the same proof. To be precise, you can even you don't even need to prove this equivalence. Why? Because you can apply equivalence of 2 and 4, conditions 2 and 4, to the matrix A transpose. Yeah, when you take A transpose, your columns and rows change places. You can apply what you already proved to the matrix A transpose, and you get this implication. Okay, this basically proves our orthogonality criterion completely. Okay, this is very handy. It's very easy to check that the given linear operator is orthogonal in every given case using this criterion. But as usual in this course, everything that we define for orthogonal, for linear transformation, we can define its counterpart for matrices. Yeah. So we define orthogonal transformations as linear operators which preserve the dot product. Then we should define what are orthogonal matrices. But we can do this using this criterion we just proved. Yeah, this gives us this definition. This is absolutely standard definition. Matrix A is said to be orthogonal if A transpose times A is identity. Yeah, square matrix. Or A times A transpose is identity. We already proved that these two conditions are equivalent, so it doesn't matter which one to check. So you can check this, or you can check this. Again, this is the definition of orthogonal matrix. So our criterion that we just proved implies that linear transformation is orthogonal if and only if its standard matrix is orthogonal. Yeah. To be precise, we cooked up this definition using this criterion. Yeah. Okay. So and vice versa, if you have an orthogonal matrix, you can remember for every matrix, you can cook up a linear operator, which is given by the multiplication by this matrix. In the previous lectures, we denoted by Gothic T subscript A. Yeah. And absolutely in the same way, our criterion implies that matrix A is orthogonal if and only if this linear operator is orthogonal. Why? Because the standard matrix of this linear operator is the matrix A. So we can apply criterion. Okay. And what we just proved, what we already proved in the beginning of this lecture, that linear operator is orthogonal transformation if and only if it preserves length of every vector. We can just translate this lemma and its proof in the language of matrices. Again, this is not a new lemma. This is translation of the lemma we already proved into the language of matrices. The lemma A is orthogonal if and only if the length of vector AX is the same as length of vector X for every X. And let me just give a proof, which is translation of the proof of the similar lemma about orthogonal transformation. Yeah, A is orthogonal by definition if length of AX is the same of length of AX. Why? Again, you just express AX. So it's basically, this is a proof of one direction. If you know that matrix A is orthogonal, then it preserves length. Length of AX is the same as length of X for every vector X. Again, by definition, you take a vector AX and take its length. But by definition, this is a root of AX dot AX. But AX dot AX is the same as X dot X. So we have here equality equals to root of X dot X. But this is by definition length of vector X. So this proves you one error here. So this condition implies this condition. To prove the opposite condition, we have to use the same trick as before. We assume that length of vector AX is the same of length of vector X for every, this is a crucial point, for every vector X in n-dimensional space. And we want to check that AX dot AX is the same as X dot Y. Yeah, because if you know this condition, this implies orthogonality. Yeah, by our criterion. Yeah, but again, we can just express it, this dot product, as we can express this dot product as in terms of the lengths of vectors X and Y. Since lengths are preserved, to be precise, here it should be two equality. It should be ax plus ay minus ax minus times ay. But then by this assumption, it's equal this. But if I didn't put extra equality because I didn't fit the width of this screen. Yeah. So, and then we get this is the same as x dot y. We already proved this earlier. Yeah. Okay. So this is another way how you can think of orthogonal matrices. And actually, you can even define orthogonal matrices in this way. Like it's matrices such that length of vector ax is the same of length of vector x. Yeah. Okay, good. Good. So let us briefly go over a few basic properties of orthogonal transformations, and then we'll consider very explicit classification of orthogonal matrices, 2 by 2 orthogonal matrices. Yeah. So first, let's state basic property of orthogonal matrices, that they determinants either 1 or minus 1. Yeah, if you have a matrix with determinant different from 1 or minus 1, this matrix could not be orthogonal. How to prove this? Basically by the definition. Matrix is orthogonal if A transpose times A its identity. You take a determinant of this of the left hand side and the right hand side in this equality, and you know the determinant of a product is product of determinant. A determinant for transpose of a matrix is the same as determinant of a matrix, and you get the square of determinant of matrix A is 1. What I just said, it's written here. Yeah. And if square of determinant of A equals 1, sorry, then determinant can be either plus or minus 1. Yeah. And actually both cases realize there are orthogonal transformation with determinant 1, for example, identity. Clearly identity is orthogonal matrix, yeah, because it's just identity times identity is identity. And if you take identity matrix and you swap sign of the first entry, of course it's going to be orthogonal matrix, and its determinant, as we know, it's going to be minus 1. Okay. And this corollary we already know. If A is orthogonal matrix, then A is invertible. I just put it here to remind you that if determinant is not 0, it implies that matrix is invertible, and vice versa. Matrix is invertible if and only if determinant is not 0. But of course, we know that orthogonal matrix is invertible because matrix is orthogonal if A transpose times A is identity. But we already know that this means that A transpose is the inverse of matrix A. We proved it earlier. Okay, and this is an example which I mentioned, just mentioned a few seconds ago in case 2 by 2. Yeah, you take this matrix plus minus 1 here and 1 here. One can check that this condition of orthogonality is satisfied. A transpose times A is identity. Its determinant is plus minus 1. Yeah. Note that this is nothing. When matrix is identity, it's just identity, but when in this example, when you have minus 1 here, yeah, this is a reflection in the y-axis. Yeah, okay. Let us briefly mention a few more important properties of orthogonal matrices that follows from definition. So first of all, the product of orthogonal matrices is an orthogonal matrix. Yeah, this basically follows from definition and properties of transpose. Yeah, you assume A and B are orthogonal. You have to check that AB is orthogonal. You have to check that AB transpose of AB times AB is identity. Yeah, you just play around. You take AB transpose times AB. Transpose of product is a product of transposes taken in the opposite direction, opposite way, yeah, like this. But now we already know that A transpose times A is identity, so this guy cancel to identity, and identity times B is just B, so this is equal to B transpose times B, but B is also orthogonal, so this is identity. So this proves this lemma. A little bit later, this year and next semester, you will learn what is a group in algebra. And basically, this lemma means that orthogonal matrices form a group, yeah, form a subgroup of all matrices with non-zero determinant. Yeah, usually this group is denoted like ON of R. Yeah, and it has a subgroup of consisting of matrices, orthogonal matrices with determinant 1. Yeah, because matrices with determinant 1, if you take the product, you get a matrix with determinant 1. Okay, and sometimes this group is denoted like SON of R, and it's called special orthogonal group of n times n matrices. Okay, if A is orthogonal, then A transpose is orthogonal. Yeah, it just basically follows from definition. And if you take lambda, any real matrix, you multiply identity matrix by lambda, it's orthogonal if and only if lambda is plus minus 1. Again, why? Because determinant of orthogonal matrices are 1 or minus 1. Yeah, so this doesn't give you much room for lambda here. Okay, so there are more properties of orthogonal matrices, but we considered probably the most basic ones. Let us consider explicit classification of orthogonal matrices in dimension n. Let us give it as a formula for all orthogonal matrices 2 by 2 by 2 orthogonal matrices. We split this classification in two pieces. First, we classify all orthogonal 2 by 2 matrices with determinant 1, and then we do the same with determinant minus 1. So we basically have two formulas, not one. Okay. To be precise, you already know the answer. We met all of these matrices already many times in this course, but let us just do it by the book, by definition. We take a 2 by 2 orthogonal matrix, determinant 1. So we want to find all of them. How to do this? Okay, you assume that A is just given by A, B, C, D. A, B, C, D are our unknowns. We have to find them. And we just translate the orthogonality into the equations of on A, B, C, D. Yeah, we know that A transpose time A is identity and determinant of A is 1. This gives us these equations. A times A transpose is identity give you this first three equations, and the condition the determinant of A is 1 give us fourth equation. So look, we have four equations, we have four unknowns, but actually you will see in a second that we're going to have infinitely many solutions. But this condition and this condition implies, yeah, if you have sum of squares of two numbers equals to 1, it basically means these numbers are on the unit circle. And it means that these numbers are cosine, sine of some angle theta. Yeah, so we can put A equal cosine theta, C equals sine theta because of this equality. Likewise, this equality implies that B and D are cosine and sine of some gamma. Yeah? Okay. Look, we already reduced, so we have these two conditions, and we reduce them basically to the fact that this is cosine and sine of some angle. Yeah. But now we use this equality, you just substitute all of these numbers here, and you get familiar formula for the angle, trigonometric formula. Yeah. So so for example, this equality for determinant AD minus BC equals to 1 applied to this cosine and sine give you this equality, but this is nothing but the sign of the difference of two angles. So we get sine of gamma minus theta is 1. Absolutely in the same way, the condition AB plus CD, this is condition that two columns of this matrix are orthogonal. Two rows here, AB and CD are orthogonal. Yeah, and this can be translated in the cosine gamma minus theta equals to 0. Yeah, you have this. And so sine of difference of these two angles is 1, cosine of difference of two angles is 0. This means that gamma minus theta differs by pi over 2, maybe plus 2 pi over k. Yeah. But now you substitute, for example, what is gamma is theta plus pi over 2, and you substitute this into this formula, and it simplifies, and you get cosine theta minus sine theta, cosine theta. Again, here we use basic trigonometric identities. Yeah, for sine of difference of two angles and cosine of difference between two angles. But this is nothing by the matrix of rotation by theta. Yeah, which we already know is orthogonal. So what we just proved that all 2 by 2 orthogonal matrices with determinant 1 are matrices of rotation. Okay, good, which is intuitively clear. Just small remark that if you forget how to basically prove these two trigonometric identities, this is a formula of sign of difference, but if you switch the sign of theta, you get a formula for the sine of sum of two angles. Yeah, and likewise here it's cosine of difference. If you switch the sine of theta, you get cosine of sum of two angles. This is proved in trigonometry, but you can actually prove it using matrices. Yeah, you know that this is a matrix of rotation by theta. If you write down a similar matrix of rotation by gamma, we know if you multiply them, then you get product of two matrices correspond to the matrix of a composition of this of corresponding linear transformation. So if you multiply these two matrices, it should be matrix of rotation by gamma plus theta. And this, if you check corresponding entries of these two matrices, you get these formulas for the sine of sum and cosine of sum of two angles, or the difference. It doesn't matter. Okay, basically what I just want to say that trigonometric formulas like this, which you probably learn in a school, can be derived from multiplication of matrices that correspond to rotation. Yeah, of two-dimensional space around the origin clockwise. Okay, good. So we found all orthogonal matrices with determinant 1. Let's do the same with determinant minus 1. Yeah. Okay. First of all, you can proceed in two different ways. One different way, you can found absolutely the same algebraic proof as on the previous slide. You just need to change sign of AD minus BC. It should be not 1, but minus 1. And you get the answer in a similar way. Of course, answer is going to be different. It's not going to be rotation anymore. Because rotation, matrices of rotation has determinant 1. But let us use a shortcut. Shortcut basically is like this. We can take any orthogonal matrix with determinant minus 1. For example, we can take minus 1, 0, 0, 1, or 1, 0, 0, minus 1, whatever. And we can multiply by our matrix A on the previous slide. Yeah. On multiply this matrix with the matrix orthogonal matrix with determinant minus 1. And then we already know that product of orthogonal matrices is an orthogonal matrix. So then as a result, you get an orthogonal matrix, but determinant is going to be 1 because determinant of product of determinant. And we already know classification of those matrices, yeah, and we can use it and we can find the formula for A. This is a small shortcut, yeah, for the proof. Let us do this. Okay, I take this matrix 1, 0, 0, minus 1, and we know that if you multiply this matrix by matrix A on left, on the right, doesn't matter, we must get orthogonal matrix with determinant minus 1. So I know that this is a orthogonal matrix with determinant 1, yeah, because this is determinant of this was minus 1, this is minus 1, so the product is 1. But I already know from the previous slide that this matrix must be matrix of rotation of angle theta. Yeah, so we have this for some angle theta. We proved this in the previous slide. Okay, and then you just need to, can you find A? You need to multiply this equality on the inverse of this matrix. Of course, inverse of this matrix is this matrix itself. So you multiply, and you get that A is cosine theta minus sine theta minus sine theta cosine theta. This is very similar to matrix of rotation, but one sign he changed and he changed. Two signs changed. Okay, quite often you can rewrite this. So, for example, rotation matrix. It's if you have a matrix of rotation, it's better keep it in this way. But to me, this matrix, I would prefer to rewrite it in slightly different way. You will see why in a second. So let me, instead of theta, introduce angle theta over 2. Yeah, call it gamma. And let me call sine gamma is A and cosine gamma is B. So we just substitute this instead of theta, we substitute twice gamma, and then you use a trigonometric formula for the cosine and sine of angle 2 theta, which you probably learned in school. Again, if you didn't, you can prove these trigonometric formulas using the product of matrices or rotation matrices. Okay, you substitute this instead of theta 2 gamma here, you simplify and you get this matrix. Okay, but then you can observe that this matrix is nothing but the matrix of reflection in the line ax plus by equal to 0. Okay. We already know how to find matrix of projection, orthogonal projection to a vector subspace. In this case, it's going to be a line in R2. If you know the formula for the orthogonal projection, you can find the formula of reflection, yeah? Because it's given just x goes to x plus 2 twice orthogonal projection minus x. Yeah, okay. This is one of the homework assignments, yeah, problems in the last homework assignment. Okay, so this is a matrix of reflection. And intuitively, it's also clear. If you have a reflection in a line, orthogonal reflection in a line, of course it's preserved distances. Yeah, you just look at the good mirror and you see that all distances are preserved. Since distances are preserved, the product is preserved, we already know this. And angles also preserved, but determinant is not exactly preserved, it changed sign. But it means orientation change. Determinant, in some sense, you will see later, it's an orientation. Left becomes right, right becomes left. You can see this in the mirror. Okay, good. So this gives us complete classification of orthogonal matrices in 2 dimensions, in 2D. Yeah, you can find similar formulas for orthogonal matrices 3 by 3. They're more complicated, of course. They're going to depend on 2 parameters. We're not going to do this. You can do this by yourself, or you can just Google. Okay, good. Let me stop